I'm gonna toss a coin until the first time that it lands heads. Okay, so I've got that's a geometric random variable, right? Okay. What's the chance that I have to toss 10 times or more until the first time that I get a head? Okay, I could calculate that, right? What would that be in symbols? So x is the number of tosses the first head. We've got a fair coin, independent tosses. Okay, so the probability that x is greater than or equal to 10 how would I actually calculate this? Get the exact number. What's the probability distribution? Okay, it's geometric with parameter p equal to half. So what's the chance? So this would be the sum from, let's say, j, we'll call it I equals 10 to infinity of so the chance it takes exactly 10 tosses, chance it takes 11, 12, 13, 14, 15. Right? Maybe better to write it this way. A half to the I minus 1 times a half. I have to get tails the first I minus 1 times, and then I have to get heads the ith time. Trials are all independent. Rings a bell? Okay. All right. So I could do that sum. Or I could take 1 minus the chance that it takes 9 or fewer. Then I would only be adding 9 things and then subtracting that from 1. But if I wanted to just very quickly get a bound using Markov's inequality, what could I do? What's the expected value of x? Okay, 1 over p, which is 2. Okay. Okay, so the probability that x is greater than or equal to 10 is less than or equal to e of x over 10, right, is a fifth. Right, it's 2 over 10 is a fifth. All right, because the number of tosses can't be negative, right? The probability that it takes a positive number of tosses is 1. This is a non-negative random variable. Okay? This is going to be a good bound? What's the chance it takes 1 toss? Chance it takes 1 toss is? Chance it takes 2 tosses is? Chance it takes 3 tosses is? Okay, we're already, this is already bigger than 0.8, right? This is 0.75. This is 0.8. We subtract that from 1. We're already below this. right? We start now taking 1/16, et cetera, we're going to get, okay, so this bound is not going to be that great, but it's still a bound. People have any idea what I'm talking about? Am I just talking to myself? I'm back to talking to myself again. Okay, let's use this little applet here to find the actual probability. Oops, where did it just go? I've lost the applet I was looking for. There it is. Okay, so let's suppose that we have a geometric distribution where the probability of success is 1/2, and we want to know what's the chance that x is greater than or equal to 10. Okay. Oh, it looks like it's actually better bound than, oh no, it's 0.195%. And our bound is 20%. Okay, so we're off by a factor of about 100. No, yeah, right. So it's not from 0.2% to 20% is a factor of 100. Okay, it's an upper bound, but it's not a very good upper bound in this case. Okay. Yes. Clarify what it means. So it is true that this probability is less than 1/5, but in fact, it is a lot less than 1/5. Okay? 100 times less. Yes?
How can we make it more accurate? If we take a bigger number?
Oh, Markov's inequality is not going to help us because this particular random variable doesn't have a distribution that makes Markov's inequality sharp. Right? The kind of distribution that makes Markov's inequality sharp only has 2 possible values. This has an infinite number of possible values. So it's always true, but it's not always a very good bound. And, yes?
So in terms of using Markov's inequality for random variables, we're trying to find what again?
If we have a random variable that can't be negative, the probability that it's negative is 0, then Markov's inequality gives us a quick and dirty way to find an upper bound on the chance that that random variable is very big. Okay, so it gives us an upper bound on a probability that the random variable is big if the random variable can't be negative. Yes?
So what we're saying is the chance that it takes more than 10 passes to get your first heads is less than
yeah, it can't be any, Markov's inequality says it can't be any bigger than 1/5. And it isn't. It's a lot less than 1/5. Okay.